When dealing with algorithms and data structures, it's important to be aware of their time and space complexity. That means that we need to take care of the time and space needed to execute our algorithm. First, let's take a look at time complexity. If we have, for example, an array of 10 elements and we need to find its sum, we can achieve that like following. We can start from the first element, its index is 0 in C#, add it to the sum, then iterate to next, add it to the sum, and so on, up to index 9, last index, and add it to the sum as well. In terms of code, it will look like following. Since we need to cover each element, we will have 10 iterations. Or if we don't have the constant number of operations, but some general n, we will have n iterations. Officially, it's big O of n time complexity, which is called linear. Further, we have some algorithms better than linear, which means that less time is needed for their execution. Binary search is one of them. We apply binary search when we're dealing with sorted array and want to check whether some target exists in the array. We're starting from the middle. Check if we found the target. If not, we proceed either left or right, depending on whether our middle element is greater than or smaller than the target one. So if we are searching, for example, 13, it's greater than 8, and we will continue searching in the right part. If we are searching for element 3, it's less than 8, and we continue our search in the left half of array. So if our array has 8 elements, like here, first we are reducing that size to only 4 elements, for example, left one. Then, if we didn't find the target, we are reducing it to 2 and then to 1. And that's the end. We either found the element or not. Or when we start with some larger number, for example, 64, in the next step, we are considering only one half of the array, then one half as well, and so on. So we will have only 1, 2, 3, 4, 5, 6 transformations, 6 steps. Here, for n equals 8, we will have only 3 steps. So the question is, when we have some input n, how much steps will we have? Let's express this n, concrete n, in terms of power of 2. So this is 2 to power of 3. This is 2 to power of 6. Here, notice that our number of steps is equal to this degree, and this number of steps is equal to this degree. So in general, we have this formula that 2 to power of steps is actually our n, which means by definition of logarithm that steps is equal logarithm of m. So that's the class big O of logarithm of n. The base is 2. This logarithm class is better than linear. So here, for example, if we have n equals 64, we will have only 6 iterations. But in linear, we will reduce it to the 63 in the next step, then 62, and so on, up to 1, and we will have 64 iterations for linear search. But for binary search, we have only 6 iterations for the same input. Let's take a look at few more complexity classes. So, earlier we mentioned a brute force algorithm for finding maximum in the array using double for loops. So if we have array like this, for each element, we need to check if it's greater than all other elements in the array. So for each element, let's start from 1 and it's our current, we need to check if it's greater than all other elements in the array. So, for example, if n is equal 5, like here, we have an array of 5 elements, we will have for index I value 0, 1, 2, 3, and 4, because we have the condition that I should be less than 5. And we stop here. But further, when I is equal 0, we have the inner for loop and we iterate through yth index. So for I is equal 0, yth could be 0, 1, 2, 3, and 4. So we have 5 iterations for only I equals 0. When I is equal 1, the same. And so on. When I is equal 4, the same. Yth could be from 0 to 4. So we have 5 times 5 iterations for just this simple example. And in terms of n, we will have n times n, which gives us quadratic time complexity. Of course, it's worse than the linear time complexity, where we have only one set of iterations, only one for loop, not double for loops like here. But let's take a look at a quick example to make the difference between linear and quadratic time complexity when dealing with the multiple for loops. So, when we have two independent for loops, I could be from 0, 1, and so on up to n minus 1. So, we have n iterations for I, and then j could be from 0 to n minus 1. So, we have another n iterations for j. So, we have n plus n, 2n iterations in total. That is big O of 2n, which is the same as big O of n. Please note that the exact number of iterations is not important. It's just important to get a feeling how large will be the number of iterations for large inputs. So, for example, here, it's not important whether it's 128 or 127 or maybe 200. It's important that it's not 16,000 like in quadratic complexity, or it's not only 7 like for logarithm. And input of size 128 is not even large. We can have a way greater inputs. So that's why big O of 2n is the same as big O of n, and also is the same as big O of n plus 1, n plus 10, and so on. Everything is about some large inputs, so such constant couldn't make the difference. Also, it's important to mention one more famous class of complexity, even better than the logarithm. It's constant class, big O of 1. That is the case for some constant number of operations. It can be 1, 2, 10, 100, doesn't matter. But the number that doesn't depend on n, size of our input. So if you have some array of n elements, and we want to get the sum of only first and second element, the size of whole array is not important for us. We will have only one iteration, array of 0 plus array of 1. So if n is equal, for example, 2 or 2000 or whatever, we will have only this one iteration. Except covered classes of complexity, let's mention a couple more in order to have an overview of the most famous classes of complexity. Remember that small inputs don't have an impact to the complexity, only large ones. For example, here, factorial complexity seems better than exponential and same as linear and quadratic, but for only n equals 16, it's way greater than others. All of them will be commented in the future, as well as different complexity classes that are not mentioned here but can occur in practice. Some of them doesn't have their own names because they are not so often in practice, but every combination of complexity can occur. For the space complexity, the logic is similar, but it shows us how much space is needed for our solution. It's expressed in terms of big O notation as well. For example, if our task is such we need to store our result in array of n elements, that means we need to occupy n places in memory. So that gives us big O of n space complexity, linear space complexity. If we don't need any additional space, for example, we just need to sum two numbers, and we don't need any additional space in terms of some large input n, it's constant space complexity. Sometimes it can happen that for some small input n, we need to generate a way greater result of, for example, 2 to power of n elements. So that's how we get exponential or even more complex classes. It can happen when we have some array and we want to find all combinations of these elements or subsets. So for array of only 3 elements, our result should contain all 3 elements, should contain 1, 2, 1, 3, 2 and 3, only 1, only 2, only 3, and empty array as well. So when input is only 3, we need to generate 8, which is 2 to 3 lists in the result. So that's how we can, from some small input, we need to store a large number of elements in the result. Here, we just briefly explain the core of complexity and how to get the feeling how many iterations we need or how much space we need and which algorithm is better or worse. In the next videos, we will go through the complexity in detail on each task we are dealing with. Wish you a happy coding!